I personally want to thank everybody. I think this is my last time up here. I want to thank our CU hosts again. It's been a fabulous town, a fabulous venue. So glad you could all be here. Thank you to the diehards that are here to the end. And we have a video, maybe, from our TREX team. Do we, Colin?
Oh, yes, I'm here, and I sent it to Ricky. So
wonderful. Well, thank you, Sanlyn. We're so glad to have you. This is a video that was collected while the TREX team was out working with their rover, and Sanlyn has put together some snips. It's kind of a trailer, and maybe Sanlyn will tell us when the full video will be available and where.
Yeah, so our full rough cut, which is about 19 minutes, can be found on our website, so trex.psi.edu. It'll be going through to add a little bit more footage from some of our scientists that had been away, and so some of that Zoom footage. But we just have a short 7-minute snippet of it to show just off a bunch of it. And I can't say enough about our videographer, Franklin Fitzgerald, who was in the field with us and put this together. So with that, I will be quiet and let it play.
Wonderful. Thank you.
TREX is NASA's toolbox for research and exploration. It's a team of 30+ scientists and collaborators, including students and postdocs. And we are part of NASA's Solar System Exploration and Research Virtual Institute, SSERVI. What we're doing as part of SSERVI is trying to advance NASA's goals in terms of planetary science and exploration. We organized TREX to have 4 themes, and they're all interconnected. The foundational one is Theme 1, and this is one where we're making a spectral library of materials that we think we'll find on the moon and small bodies, asteroids in the solar system. What's really special about TREX is that we are taking reflectance data, measuring spectra and figuring out what these samples are made out of, from the short wavelengths in the UV, the ultraviolet, all the way out to long wavelengths in the mid-infrared. And this has never really been done before.
A lot of spectral libraries that have been developed so far use very coarse crystalline material, like 750 to 1,000 micron sample sizes, sort of like a very coarse sand. But we're very interested in the dust-sized particles, so we're going really, really fine by crushing our samples to sub-10 microns or 25 micron sample sizes, so that we're looking at powder, basically, or dust. And the reason we're doing that is because the moon and asteroids and the Martian moons and other places that we might send humans do have some fine dust components. So we're trying to not just ignore the dusty remote sensing data, but we're trying to see if we can interpret it and maybe find out something more about those surfaces before we send humans to explore them directly.
So this spectral library is going to be really important, not only for the TREX team, but for the whole planetary community to use in understanding their spacecraft data and eventually even their landed instrument data from the moon and small bodies. Then we get to Theme 2, which is where we're studying the moon.
I am very happy to say that I am the lead of Theme 2. We incorporate a very wide variety of studies. Of course, looking at the ultraviolet and the very near infrared studies. We also are very interested in understanding the distribution of regolith grain sizes, and in particular where our very fine grains are located.
And then Theme 3, we're studying small bodies, asteroids. There's all sorts of different asteroids out there. Some are more rocky, some are more carbonaceous and volatile rich. The more we can characterize these, the more we can better understand them before sending future missions to them. So themes 1 with the spectral library, 2 studying the moon, 3 studying the small bodies are all leading up to Theme 4, which is our fieldwork theme. And that's what we're doing here now this week.
Zoe is a solar-powered robot, so it's able to, on a sunny day, operate continuously, generating power from that panel. It's a fairly large panel. You see it's about the size of a queen-size mattress. The robot has a number of autonomous capabilities, but one of the first things that we developed is autonomous navigation. So it starts with a rough map of the area and what its goals are, places to reach, and then it uses onboard cameras, it has stereo cameras. And recently we added a laser scanner to the robot so it can use those two sensors to model what's immediately around it so it avoids obstacles as it's navigating off towards its goal. The scientists often have goals that they think are important places to go. And sometimes those are actually places where a couple few measurements, you know exactly what's going on. There's not a lot of uncertainty. So, it's kind of natural. We want to check out the things we know. We want to sort of feel good that we were right about that. The robot doesn't have any of that kind of bias. In fact, it only wants to go look at things it doesn't know anything about. So it's driven entirely by that uncertainty. So what we found in the experiments already is that the scientists will go a particular path and the robot will maybe hit a few of those points, but also go to other places. And scientists want to do this as well. It's just a slightly different strategy, like what do you want to do first and what do you think is most important?
Instead of asking for 5 gigabytes of information from a rover, we'll be able to solve a problem, and therefore instead of sending us back that 5 gigabytes of data, it can just send back the answer, maybe 100 megabytes of data, to tell us what we wanted to know from that spot, from that location.
Ultimately, you want autonomous navigation on other planets because it basically is much more efficient than having a human teleoperate a robot on that planet. It takes a long time to communicate to Mars. So when we on Earth say, go to this point on Mars that's like 200 meters ahead, it actually takes a long time to communicate that, and then for the robot to do that, and then for the robot to communicate back, hey, I did the command that you did. So working towards autonomous navigation is working towards basically more efficient robots for planetary exploration, where we could say, take this longer traverse, and then the robot itself can do that. And it's not waiting for human communication to tell it what to do.
Overall, it went really well. It went very smoothly. The rover followed an interesting path. At first, it was kind of similar to the original path that the science team designed, and then it diverged a little. It went farther to the west, trying to look for different rocks. And it was pretty interesting because when we had the science team debriefing, the science team started to conclude that the area probably had a lacustrine or marine origin, and our rover was able to conclude that as well. So it was very, very impressive.
We're also collecting an incredible amount of very good data from all these instruments. The data are probably going to be used by the team for different publications because there's a lot of new discoveries here. This site that we talk about has not really been studied all that much. So our understanding of the geological history of this site from a robot perspective and using robotic instruments is going to be interesting to see where that goes. And basically, once we're done with that, the data will be available to the public as it should be.
The TREX concept allows us to kind of put all of these things together because, we're doing multispectral studies, we're thinking about applications to the moon and small bodies, and then kind of putting it all together in this field work to really make it happen in kind of a real-world environment. So I think it's really useful for us as a learning experience, but I think it will also ultimately be useful for NASA and other space agencies in figuring out how are we going to do this, sending humans to the moon? How are we going to make it work, and how are we also going to get great science?
Thank you. That was excellent, and I encourage everyone to take a look at the draft that's up now and the final one when it comes out.